In this session, we'll take up the design of columns. So this is the first example, and there's a column of effective length 8 meter. This is the effective length what has been given here, and is subjected to a factored axial load of 325 kilonewtons. And you need to design the column using a steel of grade Fe410 and Fi equal to 250 Newton per mm square. So before you proceed to the design, we can either go for assuming the suitable design compressive stress, or even the slenderness ratio can be assumed, and from that we can obtain the FCD, and then we can go for choosing a section from steel table. And also we can choose a trial section from steel table, check its strength. If at all, if the strength is more than the load what is coming on the column, then you can adopt that, or you can revise the section. So this is a trial method. Okay, you can try with the FCD value, or you can try with the KL by R, that is slenderness ratio value, or even you can directly go for trial section. So here I'm trying with the slenderness ratio. So the slenderness ratio, for assuming a slenderness ratio, we need to look into the load what is applied on the column, and also its effective length what we are having. So if I have a heavy load, or effective length is more, or it may be a column with a higher effective length and a higher load. Okay, so in this case we'll go for a slenderness ratio of somewhere 150, close to 150, or higher slenderness ratio. This is the range what you can choose for rolled steel section. If I want to design by assuming a suitable slenderness ratio, I'll be assuming the slenderness ratio between 100 to 150, or sometimes even I can go slightly below this up to 90. So this is the range what you can keep in your mind for assuming slenderness ratio. So if you have a column of smaller length, say somewhere less than 4 meter, if the effective length is less than that, then you can stick to 100 as your slenderness ratio. And with the increasing length of the column, so you can move towards 150. Okay, so here my column length is 8 meters, and I've chosen 150 as the slenderness ratio here. Okay, so even the load will also matter in this case. If you have a light load, heavier load, go for choosing a higher this one value of slenderness ratio here. Okay, so this will be the slenderness ratio what we have adopted, 150. Now with this slenderness ratio, assumed slenderness ratio, and the effective length what is given to us, with that the required radius of gyration will be 53.33. Now in the section what you are going to select, this will be the least radius of gyration what you will be looking for. Okay, if I select a rolled I section, I'll be choosing I section with Ry equal to or greater than 53.33. Okay, now look into the steel table for a column for Ry, where you come across a radius of gyration more than 53.33, select that particular section. So this section, that is ISHB 250 at 500.3 Newton per meter, is having a radius of gyration Ry 54.9, which is more than what is required in our case. So I adopted this ISHB 250 at 500.3 Newton per meter. Now properties of this section are: area of the section is 6496 mm square, height or depth of the section is 250 mm, width of the flange is 250 mm, thickness of flange 9.7 mm. Okay, so for, next is we need to know what is the buckling class of this section, so that I can use the proper table in the IS 800. For knowing the buckling class of the section, we need to have this H upon BF ratio and the thickness of flange. So in this case, H upon BF comes out as 1.0, and the thickness of flange is less than 100. Flange thickness here is 9.7 mm. Now the buckling class, if I go to table 10 in IS 800, with these value, I have the buckling class given over there. So this is the roles section what we have chosen here, and our case is h upon bf is less than 1.2. What value we have got is 1.0, so it is less than 1.2, and also thickness of flange is less than 100 mm. In our case it is 9.7 mm. So here the buckling class about y axis, okay, y axis is c. This is the buckling class what I'll be selecting here. My radius of gyration about z axis is higher than the radius of gyration about y axis. So the most critical is about y-axis. Buckling, if at all, if it takes place, it will be first about y-axis. This is the weaker axis over here for the buckling. So I'll be choosing what is the buckling class about this y axis, about the minor axis. So it is coming out to be C over here, buckling class C. Okay, this is from table 10 in page uh, of IS 800. Okay, page has not come here. Refer to table 10 of IS 800 2007. Okay, now with that, what we have is what is the actual slenderness ratio. Since what radius of gyration was required was 53.33, we have adopted a section with the radius of gyration higher than this. Okay, so what will be the actual slenderness ratio, that is actual KL by R? It will be 8000 effective length, 8000 divided by this radius of gyration of the section what we have adopted. So 8000 divided by 54.9, so this comes out to be 145.72. Now for 145.72, we need to find out what is the design compressive stress. So here buckling class is C. I'll directly go with table 9C, which gives me the FCD value, design compressive strength stress over here, FCD. So buckling class C, table number 9 or table number 9C. In that, for Fy equal to 250, we have values given for KL by R equal to 140 and KL by R equal to 150. Okay, so for 140 it is 66.2 and for 150 it is 59.2. I need to interpolate for our KL by R of 145.72. So with these two values for 140 and 150, FCD has been interpolated here. Okay, so 66.2 for 140 minus 59.2 for 150 divided by 150 minus 140 into, we require it for 145.72, 145.72 minus 140. Okay, in this 66.2, this has to be deducted over here, or so this is how you actually get that value for KL by R of 145.72. Okay, so this FCD value is reducing with increasing KL by R. So 66.2 for 140 minus whatever we have interpolated for this 5.72. Okay, this value of 5.72, that has been done over here with this interpolation. So on doing that, the value of FCD what we will get is 62.19. This is in Newton per mm square, 62.19 Newton per mm square. So this multiplied by the area of the section will give us what load it can carry. So 404 0.02, 6496 is the area of the section into 62.19. So this comes out to be 404.02 kilonewton. So this is more than the applied load on the column. The factor load which was applied on the column was, it was given as 325 kilonewtons. So what we have here is 404 kilonewton is the load which can be carried by that column. Okay, so this is safe. What section we have provided here, ISHB 250 at 500.3 Newton per meter, can be adopted for this column. Okay, so this is the way in which you need to proceed for designing the column. This is purely a trial method. You need to try with different value of FCD or different value of KL by R, or you can directly choose the section also, different trial sections. It is better you go ahead with choosing either FCD or KL by R, assuming FCD or KL by R. Okay, so this is some range what I have given here. Okay, for road sections, this will be the range in which your KL by R can be assumed depending on length and the load what is there on the column. Okay, with one or two trial you will have a judgment of choosing this KL by R. So that is the for a column. Now coming to one more example here. This is about a truss member, a single angle strut. Okay, so normally a single angle strut, what if at all if it is loaded through one of the leg, then we need to when we are about to design that, this is what we can have the procedure over here. So what we have is the design a single unequal angle strut of length 3 meters and subjected to a factor compressive load of 50 kilonewton. So there is a single unequal angle strut that has to be provided. The length is 3 meters. So and the load which is coming in that member is 50 kilonewton. This is factored load given to us, and the member is to be connected to a gusset plate of 10 mm thickness with 2 bolts. Okay, number of bolts used in the connection are 2. Okay, so we'll start with that design over here, and the design compressive strength has to be assumed here in this case, because we are coming across the equivalent slenderness ratio in case of single angle struts. What we'll do is we'll go with a trial FCD value. Okay, so normally FCD value in case of angle struts, okay, single angle struts, you can go with the value of somewhere between 60 to 90. So very rarely it will be up 90 and above, because they have angle sections, they have a radius of gyration are very small. So this will be the range in which you can choose your FCD value. Okay, now once we adopt a FCD value, we'll come to know what is the area that has to be provided for that section, for that member. So here the load given is 50 kilonewton, and the required area comes out to be, what I have done is I have assumed a FCD of 60 Newton per mm square. Okay, so required area will be this factored load divided by 60. So what area is required in this case is 833.33 mm square. Okay, now this is one trial section what I have chosen here, ISA 100 by 75 by 6. It is told that to design an unequal angle section. So I have chosen a unequal angle. Both legs are of not same dimension. 100 is one of the leg, 75 is the other leg. So this area, what is the area of this section is 1014 mm square. So what is required for a FCD of 60 Newton per mm square is 833.33. So I have chosen a section with the area higher than this. So area is 1014 mm square. R minimum will be RVV. There will be inclined axis what you will come across in steel table, RUU and RVV. Compare the radius of gyration of all the four axes, about all the four axes X, Y, V and U. Okay, in this case in angle struts we'll be requiring this RVV. So choose this RVV value 15.9 mm. So RVV is 15.9 mm. Width of one of the leg is 100 mm, other leg is of 75 mm width, thickness is 6 mm. Okay, so in this case, since two boards have been provided, and what we have is the condition at the end here, it is assumed to be fixed. So from that, in this table 12 you'll get to know what are K1, K2 and K3 values. So for two or more than two boards and fixed and condition, K1 is 0.2, K2 is 0.35 and K3 is 20. Okay, now calculation of lambda BB and lambda phi. So L, the distance between the centers of connection, or whatever the length is given to us, that will be taken as this L. So it is 3000 mm, and RVB for this member is section is 15.9. Substituting for these in this equation, what we have is the lambda VB value comes out to be 2.123. Similarly, lambda phi, which will be B1 plus B2 divided by 2T divided by epsilon into root of pi square E divided by 250. So epsilon, it is root of 250 upon Fi, which will be 1 for our problem. Okay, so substituting this B1, B2 and T in this, lambda phi will be 0.164. Okay, so on substituting K values and lambda VB and lambda phi values in lambda E, which is given by root of K1 plus K2 into lambda VB square plus K3 into lambda phi square. So this will be the value of lambda E, 1.52. Okay, so on getting this lambda V, go for calculating phi value, which is given by 0.5 into 1 plus alpha into lambda E minus 0.2 plus lambda E square. Okay, So this will be the value of phi, which is 2.319, and FCD is given by Fy by gamma m naught divided by phi plus phi square root of phi square minus lambda e square. Okay, so this comes out to be 55.85 Newton per mm square. Okay, no doubt this is coming out to be less than what we have assumed value was 60, but what area we decided there, we went for choosing a area higher than what is required. So in this case the load carrying capacity will come out to be more because the area is chosen on either side. Even if FCD comes out to be less than what we have assumed, if you choose the area properly, little bit higher side, then you don't require to go for any revision in that case. Okay, so in this if you substitute for A and FCD, what we have calculated here, A area of the section was 1014 mm square into 55.85. So this is giving us a load carrying capacity of 56.63 kilonewton, which is more than the applied load of 50 kilonewton here. Okay, so if it is a case of angle struts, then you decide what will be the FCD. Assume a FCD value between 60 to 90. Then find out what area is required, because the load will be given to you. What is the load which is coming in the member? So that is given to you. So that load, factored load divided by this FCD, what has been assumed, will tell you what is the area that you have to select, or the section what you have to select. Okay, based on this area, choose the proper section. You can increase this area by 25%, so that we don't have to go with a more number of regions over there. So based I like that, you can fix up the area and choose the section over here, and knowing the properties of this section, go for calculating equivalent slenderness ratio and the FCD value, and finally check what will be the load carrying capacity of that member with that section what has been provided. If that load carrying capacity is more than the applied load, then it is safe, you don't have to do any revision, you can adopt that section over here.